Welcome to this introduction course on combustion. My name is Thierry Poinsot, and you can find me at this address if you need to ask questions for this course. Combustion is an interesting science, and probably many of you have heard about combustion before, but never realized how important it is for our society today. So there is a simple point about combustion is that 90% of the energy on Earth today is produced by combustion. Every time you get 1 watt somewhere on this Earth, it's by burning something. Something could be hydrogen in a very sophisticated rocket engine, for example, but it can be also just burning wood to get some hot water if you live in Africa. Whatever you do, it's always with combustion. So it's really the first engine in our society. So if you would suppress combustion, there's a small list here of things you would have to live without, and you can see that it would be very difficult to live. Actually, the whole society would collapse if combustion would stop tomorrow. Just a few examples. All of you know about satellites, but you know satellite is basically first a combustion fact. It's this kind of things you need to propel satellites up to the place where you need them. Combustion is also this kind of things which is not only useful for a society, it's also a lot of fun. This is the simplest example of where you can have fun if you are an engineer. So these pictures give you an idea of the power which you can find in an engine like this. By the way, those are French engines. Everywhere here, you find combustion. The rule for such an engine is simple. It has the power of a nuclear power plant in the volume of a car engine. Of course, it lasts not very long, usually 200 seconds, and that's the end of the story. But still, this is the kind of funny things you can do when you work on combustion. Now, combustion, those are other pictures here. Those are normal operations, and you can see how important it is here to master the process which leads to this kind of power. Sometimes these things get out of control. You will see a picture in a few seconds where things don't burn the way they should. So now, this is normal, okay? You're going to see something which is not normal in a few seconds. And this one, for example, now this is not what should happen. This explains why everyone is sitting about 200 meters away from the rocket when you start it. Now, I'm not going to spend a lot of time in this course on military applications, but obviously military, army, everything there is about combustion. Rockets, missiles, bombs, everything here would not exist without combustion. That would be a good thing, but you don't have a choice. So the aircraft of today, the aircraft of tomorrow, and even the famous problem of terrorism, you hear about this every day now. You know, it's not that it's difficult to do a bomb, but what is difficult is to send it where you want it to go. And that's much more difficult, and it's, again, a combustion problem. So I will forget now about army applications, just come back to your everyday life. So I want you to remember two basic equations in that field. The first equation is the following one. There will be equations in this course. Today there will be only simple equations, but after that you will see much more equations. But the simplest one is that the energy on Earth today is combustion, and I think most of you realize that. What you don't realize is that the energy on Earth tomorrow will also be combustion. It is clear that renewable energies, you hear about wind and sun every day, they will replace combustion, but that will take a very, very long time. You will probably be retired by the time this happens. And also, they will not be able to replace combustion for everything. You cannot propel an aircraft with sun or wind. This will never happen, whatever you do. So for a long, long time, combustion will remain the first energy source, whatever we do. Just to give you an example here, this is the way they produce electricity in the United States today. And if you look here at the natural gas plus the coal, it's more than half of the energy is obtained by burning something. And the renewable energies here are very small, about 4% or something like this. So in France, it's a little bit more. It's more like 10. So these things will increase, and they will increase fast. The market for renewable energies grows extremely fast. The problem is that it's very small today, and the problem is that the global demand for energy grows faster, which means that in the future, not only the renewables energy are going to grow, but combustion also will grow. We'll build more and more power plants using combustion as an energy. For example, the market for gas turbines keeps growing all the time. So it's very important to realize that the business for combustion will be there, and you will be retired by the time it stops. So our problem now in terms of combustion science is that we must allow this to happen without increasing the emissions, without wasting fossil fuels, and of course without making climate change worse, because as you know, combustion is the source of a significant number of problems here. Pollution, you heard about that before. This is something that we've been working on for a long time in the combustion community, and of course we cannot live with that. If we keep increasing combustion without limiting pollution, we'll be in bad shape. This is coming from Toulouse, actually. This kind of pictures is not something we like to see in Toulouse, where we build aircrafts. But the question is a valid question. Is it possible that we are, for example, changing the climate because we are flying? And that's something we also need to understand. And combustion extends beyond the engine. We also need to know what our engines are doing to climate. For example, this is a picture taken also in Toulouse. You know that aircraft leave contrails behind them. Contrails are like little clouds here, but these clouds can grow, and in certain parts of the world, at certain times of the day, more than 50% of the cloud comes from aircraft. And an interesting question was, does this change climate? To do that, it's very difficult, and one experiment that you have to do to make sure is to stop aircraft for a long time. Of course, you cannot do that except in certain circumstances. For example, after September 11, there was no aircraft in the United States for 3 days, and during these 3 days, they observed, this could be due to random fluctuation, but still they observed very large, much larger difference of temperatures between the day and the night. So this is a suggestion that when you put all these aircraft in the sky, you modify the cloud, and so you modify the climate. So you see combustion science goes from outside the engine, and also, of course, I'm going to talk a lot about that, about inside the engines, and this is what we need to master. This is what I'm going to try to teach here. So pollutants. There are two main types of pollutants. In this course, we're going to burn a lot of hydrocarbons. So it's molecules where you find N carbon and MH atoms. You burn them with oxygen. It gives you CO2, water, and a few other things here. These things here are the things that can be avoided. CXHY is an hydrocarbon which you did not burn completely. These kind of things you smell on an airport, for example, kerosene. CO, NO, all these things are due to a combustion which is not perfect. And so those can be avoided. They should be avoided. CO, for example, would just kill you. If you have too much of CO in a room, you're going to die in a short time. So, of course, you must avoid it. And the progress here has been impressive in the last 30 years. And 10 years ago, the objective was to diminish those things. Now the objective is different. We also want to diminish CO2 and H2O. CO2 and H2O, if you burn hydrocarbon, one molecule of that will necessarily give you N molecule of CO2. You cannot avoid that. So the only way to decrease now the emissions of CO2 and water is to maximize efficiency. That means we need to build engines which consume as little as possible of hydrocarbon if we want to minimize the impact on climate, because CO2, of course, is the main problem for climate. And the progress in the combustion field has been huge in the last 20 years. In the field of piston engines, for example, the efficiency has increased by a factor of 2. Now, I see a lot of people, especially young people like you, wondering about if I'm doing combustion work, am I doing something dirty? You know, actually, it's just the opposite. Today, if you want to do something useful for the planet, you need to work on combustion, because combustion will be here for a long, long time. There's just no way to avoid it. Well, there is one way to avoid it. You can stop driving, you can stop flying, you can stop heating your house, and you can stop eating also. You can stop a lot of things. If you do that, you don't need combustion. If you want to continue living like you do, you just know the way. So we need to work on combustion because it has a very strong impact on society, and also because today it's a very sophisticated technology, so we need a lot of engineers. This is why you are here. Now, combustion is also politics. this is an example here of the years and the regulations giving you the amount of CO2 per kilometer in a typical car. And you see that, for example, Japan and European Union are pretty low. You can see that every time you buy a car in France, for example, that you are looking at these numbers and you get taxed if you do something which burns too much fuel. But here you can see, for example, in the United States, that the ratio is almost 2. So it's not a problem of technology here. It's a problem of politics. You have to decide you want to drive a small car or you want to drive a big car. So you see also where it's not only science. You know, there's also an impact on the politics, which is very strong. I'm going to take some words, because this is something you hear about on TV almost every day at the moment, about the link between what we burn and the change of climate. This comes from a very good talk given by Professor Sawyer 2 years ago. And Sawyer was basically addressing the question of the link between combustion science, what we do, and climate. So just to remind you of a few facts, the idea that combustion would change the climate is not new. Fourier, already two centuries ago, said that this was possible, and Arrhenius, and you will see Arrhenius many times in the field of combustion. Arrhenius did a very simple computation. You can do that on one page. And he suggested that if you double the CO2, you change the radiation balance between the Earth and the sky, and then you can raise the temperature of the Earth by 5 degrees. Now, you can do that on one page. If you want to be more precise and take into account the ice, the atmosphere, the ocean, you take about 2,000, 3,000, 4,000 people on Earth. It's called GIEC here. And those are all people building models to predict climate. And, but the conclusion is always the same. If you release CO2, you increase the temperature of the Earth. And of course, you know that as the temperature of the Earth is going up, the place, for example, here where you find ice on the pole is shrinking, and the amount of ice which is left on the pole is going down, and you hear about this problem every day on TV. Now, the question is, are we responsible or not? Lots of people are showing you this curve. It shows that CO2 is increasing versus time. Okay? This curve as itself is not very impressive. This one is much more interesting. If you come back 10,000 years ago and you look at CO2, you can see that something is happening here. And what is the time here? Well, it's just the time when we started burning coal and then gas and gasoline and kerosene. It's difficult to explain that this is not our fault. Okay? This is combustion. It's just no way out. And if you compute how much CO2 we release by combustion every day, you find exactly the slope which is here. So it's really a simple model. There's no big discussion about that. We are the cause of the problem. So we need to do better in the field of combustion. Now, combustion has other problems. Even if you don't want to do combustion, you're going to have to fight combustion in many places. If your engine has a problem, here you see a nice hole in a combustor. And also, if you have fires, you have to fight combustion. You need to understand how these things propagate, for example. There's a long list of places where you get into problems with combustion. This is basically the world of combustion is split in two parts. People like me who are trying to get good combustion, and the other people who try to have no combustion. All the people working in that field try to avoid combustion. But of course, you know, it's just not possible. For example, if you're flying in this aircraft, suddenly you are very interested in combustion science. You'd like to know what's going on. You know, the French had this rather dramatic problems with combustion again here, and this is a typical problem where combustion science could have helped if we would have included in the design of the aircraft. An example also of electrical safety, something which is not as known. If you take a building or even your house, for example, and if you have a leak here of gas, this can happen, so you can have gas here mixed with air, so this thing can explode. Usually, why does it explode? Well, it explodes because you get an electrical spark somewhere. For example, in the place where you have all your electrical connections, you have what we call here an electrical box. And the problem is to design this electrical box so that if there is a mixture here, and if you ignite it because there is a spark, the flame will stay within this box and will not ignite the whole building. There are lots of people working on that. And so you have many solutions. One solution, for example, is to design a box here, which is really able to keep the flame inside. If you do that, this box might have problem of structure. That means it could explode because the pressure will go up. So what you do, you put a small hole here so that the flame can go out. But the flame should go out, but a very limited amount of flame, because if you have a large flame coming out, then of course you will ignite the whole building and it's lost. The other solution, of course, is to have a box where nothing can come out. Then the flame will start, it will go up, and then the problem quite often is that the pressure will go to a large value and that the box itself will explode. And so it's a problem of design to be in between these two situations to make sure that if you switch the light on and you have gas, then nothing explodes. Difficult combustion problem. Just a few words about deflagration, detonation. You hear that on TV. Basically, they get it wrong all the time. There are two main categories of flames. One is called deflagration. I'm just here mentioning the name, the sound you will hear. Basically, for a deflagration, you will hear no sound. When I will ignite flames here, you will have no sound in this room. So, and the pressure in a flame like this is almost constant. The pressure in the burnt gases, the pressure in the fresh gases, it's the same. A detonation is a boom. So a detonation is basically a flame plus a shock wave. You have heard about shock waves in the course of aerodynamics. Here, you get a shock plus a flame pushing the shock. And of course, and that's not very pleasant, deflagration can become detonations. I will just now show you a few examples that's probably simpler to understand. So that's a building. Again, this problem appears really in safety. So you take a building. It's not a real building, okay? It's for an experiment because they put gas here with air, simulating, for example, a leak in the gas ducts. And then they're going to ignite it at one end. And here, the system will lead to what we call a small flame or a deflagration. Okay, it's not pleasant if you are here. Okay, obviously everyone in this building would be killed, but that's okay. I mean, it's not our problem. Our problem is the building itself, because imagine that this building can be, 20 floors high. So our problem is to avoid that the whole building collapses. So if you have deflagration here, you have basically a flame propagating from this side to this side, and it remains a deflagration. There is no shock. Another one. You can imagine here the size also of this experiment. This is real size, okay? So you can imagine the cost also. So this is cool. It's just a deflagration. Let me show you a detonation. Detonation is more interesting. Now, the system is such that this deflagration will transition to detonation. And when it does, you have this kind of result. So now, everyone is dead inside, but the whole structure is gone because the shock puts a lot of pressure on the walls go away, everything collapses, so everyone is dead there. Not only the people here, but everyone in the building. So being able to predict whether you go to detonation or not in a building is very important. You had an example not long ago in the oil industry. You remember, as soon as you get an explosion in a system like this, you get into a lot of problems. So we need better combustion systems, more reliable, more efficient. The problem is that that's not so easy to do. First thing is that the combustion technology today is already very complicated. I'm just going to show you a few examples here. That's a piston engine, 4-stroke. So you get the piston, you get valves here for intake and exhaust. I have brought actually 2 of them, so you can take a look at them. In the old days, all the students were able to work on their own engines. I know today very few of you have ever seen that. So that's a piston, an example of piston engines. I broke them myself. So the technology here is extremely complicated. If you start working on a piston engine and you want to improve it, you will find out that many people have worked on that before you, and that's not so easy to do better. Just to give you an idea also of the complexity now, this is a 4-cylinder system with, you can see the velocity field here at the intake and at the exhaust, and you can have an idea of how complicated it is to tune something like this. This used to be like an art, now today it has to become a science to be able to get all the waves. You get a lot of acoustic waves here propagating everywhere. And so this is a very complicated field. So if you have an engine and you want to do better than what is existing, you need to do something really good. Now the problem, of course, also is that even if you are able today to build a better engine, the cost of replacing the existing technology by another technology is very, very large. If you think, for example, of engines like this guy here, this is an engine for a boat. You can see the size of the guy here. This kind of engines, if you come out with an idea and say I can do better, well, the cost of replacing this engine by another one will be a very large cost. Furnaces, you know, we need to heat a lot of things for process, and of course we do that with combustion, with flames, very long flames here. You can have things here of the 10 meters long, 20 meters long for the flame, and optimizing this thing is extremely difficult again, but the consumption of these things in terms of gas and in terms of pollution is huge. So again, here we have to do something to help. Gas turbines. Okay, I'm going to talk a lot about gas turbines today because they are very important. Gas turbines, there's just no other way to propel, for example, an aircraft. You cannot use any kind of other energies to do that. So it's very important, and it's also very important for electricity. Electricity today is produced by many ways, but typically when you talk about renewable energies like wind or sun, there are problems with these systems. There are days where there is no wind or no sun. So what do you do when you install a system producing energy with wind or sun? You need to buy also a gas turbine, because the customers, they want electricity even if there is no sun or no wind. Especially in the summer, which is being now the first problem quite often is the summer, because people use air conditioning. On a very hot day without wind, then you will have to be able to do something. And so you will need a gas turbine. So gas turbines are found everywhere. You can find big gas turbines, small gas turbines. I'm going to show you a few examples of these animals. This is a gas turbine which has been very good for France. This is CFM56. If you're flying on an Airbus 320 or a Boeing 737, certainly you have been propelled by this engine before. Just to show you how these things work, you get a compressor here. The combustion chamber is this small thing here, and the turbine is behind it. Why do you need a compressor? You need a compressor, if you remember your courses on thermodynamics, because you are much more efficient if you burn at a high pressure. So here, the goal is to increase the pressure to 10, 20, 30 bars. You burn in the combustion chamber, and then after that, the turbine recovers the energy produced by combustion. But as you can see, this is an old engine. It's already quite complicated. Now, gas turbines come in all sizes and powers. Here you get a reasonably big gas turbine. The power is of the order of 300 megawatts. So if you put 3 of them, you get a nuclear power plant. So it's a very large, very powerful system. At the other end, you have here a very small gas turbine, about 50 watts. In between, you get all the range. So you can cover almost everything in this world with a gas turbine. Just an idea of what this is. This is what we call microturbine, and some of you may actually work on that. There was a student from ENSEEIHT working on that a few years ago. And you can see inside here, you get also a compressor, turbine, and a combustion chamber. Everything is very small. What is the objective here? Well, basically, and this is a very important statement here, if you burn 100 grams of methane, for example, CH4, it will produce much more energy than what you can have with 100 grams of an electric battery, typically 15 times. The first wonder of combustion is that with a limited amount, a limited weight, you can have a huge amount of energy. And so what is the application here? Well, like always, like often, it's a military problem. You know that if you want to win a war, you need to be able to have the soldiers on the field for 3 days, typically. 4 days, 3 days, well. For the man, it's a problem because after 2 days, most men like to sleep, but you can play games with that. You know, you can inject them a few things which make them work for an extended amount of time. After that, they will die, but you don't care. The problem is that if they work and they have no weapons, it won't work. What do they need for the weapons? They need electricity. They need electricity for the GPS, for the radio, for the communication, for the weapon systems. And if they need to carry batteries on their back, it just won't do the job. They will have like a car battery on their back. So the weight is a problem. So the military here are paying to see if they could, instead of giving them battery, they would just give them methane and burn that in a very small system which they could carry on their back, for example. And this would be, as you've seen, big like this. If this works for the military, then it will work for you on your cell phones. Instead of having batteries, you will have things like this. And instead of having to plug your cell phone every 2 days or 3 days, you could just go like to the shop every 1 month or 2 months just to add methane into your cell phone. So this is another field of application of combustion. Now some people have fun also with exotic turbine. I've actually seen even a turbine on a bicycle. There's no useful application of that, of course. An idea of how people are working today on computing those things. This is an example taken from Stanford where they compute a complete gas turbine with the compressor here, the combustion chamber, and the turbine here. The progress in the simulation field in the last 5 to 10 years has been so large that we start being able to do these computations. So you can see here a result of the computation. To do that, you need a lot of processors. It's not something you do on your PC. You need a room filled with PCs, typically 10,000, 100,000, 1 million processors pretty soon working together to do this computation. Many of the students doing thesis, for example, in the field of combustion will actually do computations very similar to this one. Now, gas turbine combustion chamber. What does it look like? Well, you have an axis here. This is the axis of the chamber coming towards you, with the turbine on this side and the compressor on the other side. Here, this is the place where combustion takes place. This is what we call the combustion chamber. And you can see here a field of temperature, for example, in this zone here. These things here are called injectors or swirlers. I have brought one of them for you so you can take a look at it. A swirler is a system which is there to mix the air and the fuel. You will see in this course, basically combustion. To do combustion, you need to mix these two things, the air and the fuel. It's like cooking. You know, if you don't mix those things, it won't work. And you need to mix them fast. So this system, as you will see, is extremely complicated. The reason it's complicated is because you need to mix things very rapidly, and you need to avoid a lot of problems I will mention in a few minutes. So this is also an expensive piece of hardware. Don't break it. So you have one here. In a system like this, you will have between 15 and 24 located everywhere here. So the air will come from this side, mix with the kerosene here, and burn in the chamber here and go to the turbine. Now, this thing you have in your hand, when it's burning, and you look at the flame here, this is what you would look like. It's like a lighter, except it's a much brighter flame. And then here the gases are cold. This is cold air. And here you get very hot gases. Typically in combustion, you will go to 2,000 to 2,500 Kelvin. Those are the typical temperature range you will have in an engine. So this is not the only thing you need to do in a gas turbine. The problem of gas turbine is that it's not only about doing combustion in this zone here. This is one sector of a gas turbine. You also need to make sure that the walls will survive. You know, if you have a temperature of 2,000 K, there's no way the wall will survive if you don't cool them. So what you need to do is to cool the walls here. And you need also to cool the walls so that to inject here additional gas so that when the air reaches the turbine, it doesn't burn the turbine. So you see here, for example, this is what we call dilution air, dilution jets. Those are cold air jets mixed with the burn gases here so that when you reach the turbine, which is here, you will not burn the turbine. So let me explain that a little bit better. By the way, I'm going also to give you this one. This is another piece of combustion chamber. This one comes from an helicopter. It's a turbomeca combustion chamber. You can take a look at its shape. You will see the small holes on the walls, which are very important for cooling. And you recognize the shape, of course. It's only a piece which has been cut. Normally, you will have, of course, the complete chamber. So for an engineer working in that field, the main question is the following one. I am injecting here kerosene. Here I'm injecting air. And here I have a turbine. The turbine will receive the hot gases directly. And the turbine, if you don't cool the pieces which are here, you will just kill the turbine. It will just melt away. So it's really a problem of cooling these things. By the way, I've also taken here a very small piece of turbine. It's what we call a vane. This is the kind of things which will have to resist to the temperature field. And you have an idea here of the size. And of course, it's a problem of what will be the temperature in this system. So it's a problem of temperature. How do you cool that? Well, as I said, you're going to have to make sure when you add here some cold air that the temperature here is small enough, low enough, so that you don't burn the turbine. So as I said, here you get 2500 Kelvin. Here you're going to have 1500, and the turbine is just behind it. If you make a mistake, you burn the turbine right away. It's the end of the engine. And if you fly in this engine, it's also a problem for you. Now, this is a picture of an helicopter engine. Helicopter engines are quite complicated because they need to be small. So the air here is entering through that side, coming here. Here you mix it with kerosene, it burns. What you see here is the temperature field. The chamber makes a turn here, and here you don't see it really well. This is the first part of the high pressure stator. This is where the turbine is sitting. So here, if you are sitting here, you receive all these hot gases, and the question is, how are you going to survive to that? Well, it's not easy. This is the same thing you have in your hands, receiving all the hot gases here. It's a problem here to make sure that you get cool enough so that you can survive to these hot gases arriving here. So when you talk about combustion science for gas turbines, our first problem is make sure that you don't burn the combustion chamber. Of course, if you burn the combustion chamber, that's the end of the chamber. It's the end of the story. At the same time, we need to minimize pollution because you cannot sell your gas turbine. And then we want to maximize efficiency and minimize fuel consumption. So the optimization of this system has been here for a long time. It's very important to say that if you look at an aircraft today, or even at a car, they all look the same. Okay? The shape, for example, of an aircraft is not something which you can really optimize much more. They all look the same because they all found the same optimal. Well, if you look at combustion chamber, they are all different. You take a French chamber, a German chamber, an American chamber, all of them are completely different. And this is a strong suggestion that no one has really found the optimum way to build a combustion chamber. They are all different. So one of the reasons for the problems here is the following, is that when we optimize combustors, we don't always get what we expected. I must say quite often we go into problems. This is an example, it's an old movie from NASA, taken at 2000 frames per second. So it goes much faster than what you see here. You have here a mixture of air and gas, and here you have what we call a backward-facing step. And here you have combustion. So you can see structures here. This is cold, and this is hot, typically 2000 Kelvin. If you take a chamber like this and you start optimizing it, you change things. One of the things you can change is, for example, the amount of fuel which you have here, or the amount of air, or the pressure, or the temperature. Quite often what you obtain is this kind of reaction. That means the flame doesn't do exactly what you expected. In this case, instead of staying where the flame should be, it goes away, it goes upstream here, and we get what we call a flashback. That means the flame, instead of burning quietly here, oscillates. This is another geometry, but you will see the result is the same. We have what we call a combustion instability. And very often when we optimize a flame, after a few tests, we get a system which is optimized but which gets unstable. And if it's unstable, you cannot use it. And the examples of combustion instabilities are everywhere in the recent life of combustion, and they are a major problem for development of many combustion systems. If a flame is unstable, for example, if a flame here goes to places where it shouldn't go, then the engine dies. This is an example of the famous rocket engine programs in the United States, the one they used to go to the moon. You can see, for example, here, this is not the design, okay? This is what happened after combustion stability. You can see the melted part of the chamber. Same thing here for an industrial gas turbine. The flame came back to this place. It shouldn't have been there, but then you basically burn all these pieces of metal. Or here, this is an injector for an aircraft gas turbine. You can see here this whole piece melted, went away. And of course, when this happens, if it's in a real aircraft, you kill people. Now, the other thing which is not good about this story is that even if you don't burn things, you vibrate the system. The combustion stabilities lead to oscillations of everything. When things start oscillating in a gas turbine, it's not good news. For example, all in the compressor and the turbine, everything is adjusted in a very tight way. If things starts vibrating, you can have a vane touching, for example, the casing, and then the whole engine will explode, and you will lose pieces, like, for example, this one here. This is a piece of an engine. This is the second engine in an aircraft which exploded, and this piece came through the aircraft and hit the other engine. So this is an example where the pilot lost one engine, and right away he lost the other one. And how did it do that? Well, this piece of engine went through the plane and hit the other side. So that's no good, of course. Now, vibrations are something you want to avoid. This is another example of bad vibrations. As soon as you get something which can create oscillations, you can go into problems. In this case, obviously, they have a problem of unsteadiness, something which is vibrating too much. And after a while, if things vibrate too much, you get into problems. I think the pilots were probably complaining about it. Now, if you do that in a lab, and you try to create the same problem in the laboratory, so this is what you do. You take a combustion and you add walls here so you can look at them. This is a picture taken at DLR in Germany. And if this flame starts getting unstable, this is what you observe. Not good. Okay, when you start having these kind of problems, you have to work on it. The nice information about that is that in the last few years, maybe 5 years now, we started being able to compute these things and to predict them. Because up to a recent time, basically, we could not predict combustion instabilities. That means we would build the aircraft, build the helicopter, try it, and if it wasn't stable, then say, oh, okay, how do we fix it? And you see that's a very significant risk, of course, for industry if you, at the last moment, you can have a big problem like this one. So again, this is a field where combustion science is not strong enough at the moment. We are not at the point where we can really make sure that we can say this system will be stable, and we still have to rely on many tests. Okay, let me show you something else now. Since we are talking about combustion instabilities, I would like to show you that these things don't require very sophisticated equipment. So this is an example of flame. So here you get gas. You can buy that for 25 euros. And here we get what we call a burner. This is a very simple burner, okay, much cheaper than the one I gave you. So the objective of this guy is just to mix air, the air of this room, with the gas here, and to do a flame. This is a burner. And this is a combustion chamber. Okay, you have to imagine it's a combustion chamber. The real chambers are much more complicated. What I want to show you now is what happens when you put a flame in a combustion chamber. Why do you do that? Well, there is no interest of having a flame in free atmosphere like that, except if you need light or if you want to waste the fuel. If you want the flame to do something useful, you have to put it in a chamber, either to recover the heat or to produce mechanical power. So as soon as you get a marriage between a flame here and a combustion chamber, interesting things may happen. So I hope I don't burn anyone today. Last time I just burnt one student, so it's just... So this is a simple flame, blue flame. You see it's nice because it's blue. When it gets yellow, it means it's making soot. We talk about soot later. And this is typical, the story I'm going to tell you is typical of what happens in industry. Industry is producing burners and chambers. So the first year, they have this burner and this chamber, and they sell it to a customer. And basically what happens is nothing. Okay, you just hear a little bit of noise because the air is accelerated in this chamber. And the second year, they have another customer asking them for a larger combustion chamber. So they take this one, and nothing happens. Okay, the flame here has no problem. And so the third year, they have sold a chamber big like this. They have sold a chamber big like this one. They're selling this one, which is just in between. If you believe in linear problems, you say, okay, if this works and this works, the last one should work too. So this is what's happening. And you see here, that for this chamber and for this chamber only, you get something new. You get what we call a combustion instability. What's happening here? Well, the acoustics of this tube in my hand are just right to get coupled with the flame. And when this happens, you get an instability, exactly like the one I've shown before. Now, you do that with a very small burner like this here, it's not a problem. You do that in an engine, and you lose the engine. So let me show you what's happening inside. Here, these tubes are not transparent. I'm going to show you what the flame is doing inside a tube like this when you get into an unstable mode. You see the flame here, and this flame is actually oscillating. So, and it's doing vortices, and it's exactly what is generating the sound that you hear. And so you can see here combustion stability is just the problem that you have an acoustic field interacting with the flame, something you don't want, or you would like to avoid, and it does not happen all the time. It happens only in certain cases. The problem is that you cannot predict it, and you can see how dangerous that is. And this is what's happening, for example, in companies like Turbomeca or Snecma in France. All the companies have the same problem. They've sold 2 chambers which were working fine with their burners. They sell a new one, which is just in between, which looks almost the same, and then suddenly nothing works anymore. The system starts shaking, and then they cannot sell the engine, and then it's panic mode. So here what they need is combustion science. So let's go to talk a little bit about science, because in the end this is going to be the topic of this course. Science of combustion is basically things that you know already. Not all of them, but many of them. It's a mixture of thermochemistry, this is thermodynamics, fluid mechanics, of course at ENSEEIHT you all know about this, transport, and chemical kinetics. I'm going to go through these 4 fields to show you what we're going to be doing in the next sessions. Okay, thermochemistry. Thermochemistry, you've done that before a long time ago. Okay, the simplest thermochemical equation is this one. You take, for example, methane, you add oxygen. Usually, we get the oxygen in 2 ways. You can buy the oxygen. You go to Air Liquide, for example. They're going to sell you pure oxygen, which is very expensive. There's another place, of course, where you can find oxygen. It's just in the air, which is nice. Which, for example, in this room, you get oxygen. The problem is you get it also with other gases. Mainly, you get it with nitrogen. And so the idea for air is that you get 1 mole of oxygen for 3.76 mole of nitrogen. This is what we're going to use throughout this course. So if you burn this thing, you're going to find CO2, H2O, and the nitrogen is just sitting here. It doesn't do anything. So this is the simplest example of thermochemical equation. Now, hydrocarbons, there are many of them. The first one, the simplest one, there is no carbon actually, is hydrogen. Hydrogen, usually we burn it as a gas. Methane, CH4. Propane, C3H8. This is what you find. Methane is what you find in your house. Propane is what you find if you buy bottles. And then you go, of course, to gasoline, which is liquid, which is what you burn in your car. And you go to kerosene, which is what you burn in an aircraft. Now, this is a very, very simplified view. If you go to gasoline, for example, gasoline is not C8H18. Gasoline is this plus maybe 300 other components. Okay, it's a full mixture. When you go to oil companies, they don't deliver pure CH18. They give you all kinds of mixtures. And usually we burn these things with air or with oxygen. As I said, we will consider throughout this course that air is a mixture of oxygen plus 3.76 moles of nitrogen or pure oxygen. Why do we take pure oxygen? Well, if you go to places where there is no air, submarine or rocket engine, then of course you need to take your oxygen with you. You're not going to carry the air. You're going to take pure oxygen. Now, classical example of things you need to know for the control. If you cannot do that, you're going to be in trouble. If you burn now in general CnHm plus O2, you can find the coefficients here. You start with the carbon. So it's NCO2, you continue with hydrogen, yes, and then you finish with O2. This you've done before. If you have air, you just add N2 here, and the nitrogen remains on both sides, doesn't play a role for the moment. So this was the simplest chemistry, the one you've done before. Now in practice, when I've written this equation here, I have assumed that I could find 1 mole of CH4 for 2 moles of oxygen. But there is no reason for that. It would be very lucky in practice if every time you find 1 mole of methane, you can find 2 moles of oxygen. In many cases, what you have is F mole of methane and 2 moles of oxygen, and F can be anything. And F is directly linked to something we will call the equivalence ratio. And if F is less than 1, we call it lean combustion. If F is more than 1, we call it rich combustion. And of course, if you need now to work on this equation where you don't have F equal to 1, you get different results now. For example, if combustion is lean, you don't have enough methane for everything you need to burn, so there will be oxygen left in the burn gases because you don't have enough of this methane to burn this oxygen. And it's the other way. If F is larger than unity, you have too much CH4 here, so there will be CH4 left in the burn gases. A general point to make here is that this is much better than that. Why? Well, here you're wasting your fuel. Okay, you have too much fuel, and fuel is expensive, so you don't want to go in this regime. And the other problem here is that when you get rich combustion, you get a lot of dirty things left in the burn gases. You get CH4 here, which goes to other molecules, CXHY, things which are not good for your health. So it's much better to work with lean combustion. What's happening in real systems? In a gasoline engine, in your car, if you have a classical engine, the values of F, the value of decons ratio is 1. It's not because of combustion, it's because of what we need to do to clean the burn gases. It could be less than 1 actually, but it's not today. So in the new engines called direct injection, there are not that many on the road today, but there are quite a few. For example, the first one was the famous Mitsubishi, probably 5 or 6 years ago now. In those engines, you can decrease the decons ratio to 0.4, so you can save a lot of fuel. In a gas turbine, you can go to 0.3 to 1, typically for the decons ratio. In a Formula 1 engine, the decons ratio is 1.2. Of course, you don't care in a Formula 1 engine about consumption. These engines burn about 100 liters per 100 kilometers, so it's not very efficient. But there is a reason for that, and we will see that in the next courses, is that this is the place where the efficiency is the largest, the flame speed is the largest. Same thing for motorcycle engine, except you cannot buy them anymore, but a few years ago you could still have motorcycle engines which were running rich. So basically it costs you a lot of money. You need to put more fuel to have the same power. Now, when I've written an equation like this, there is something I did not discuss. I said, I have these things, I ignite them and then burn, and I got these things. And I never cared about the speed at which this reaction takes place. And this is an important question. Why is it important? Well, because if this speed is too low, it will never happen. In an engine, you get a certain size for the engine. The combustion has to take place within the engine, not outside. Okay? If it's outside, it's too late. So it's very important to know how fast you go from one state to another. And this is the field of what we call chemical kinetics. Chemical kinetics, the objective of this science, it's not something I'm going to go into details here because it's a complete science in itself. Its objective is to tell you how much time you need to go from here to there. It seems like a simple question at first, but if you think it's a simple question, you're going to be in trouble later, because if you want to understand how these things happen, then you need to go into many more details. So let me just take the simplest of all, which is hydrogen. The reaction of combustion of hydrogen is simple. You take hydrogen plus oxygen gives water. Nothing simpler than that. In practice, these things never happen. In this world, if you mix and burn hydrogen and oxygen, you will never have this reaction. Never happens. What's happening is much more complicated than that. And this is the field of chemists. The chemists, what they tell you, okay, if you want to talk about hydrogen, oxygen chemistry, you need to realize you need to care about elements here, hydrogen, oxygen, and nitrogen. And you have not only species which are hydrogen and oxygen and water, but you have to care also about all these guys here. And if you want to talk about reactions, those are the reactions you need to take into account. So you see, for example, H2 plus O2, when they meet, they will not do water, they will produce OH, 2 molecules of OH. Then this OH, when it meets H2, will do H2O plus H, etc., etc. And you need to care for all these reactions at the same time if you want to predict how the global reaction takes place. Of course, at the end, if you start with 1 mole of hydrogen, 1 mole of oxygen, you will end up with 1 mole of water. But in between, all these things will have been formed and will have disappeared. And to predict the speed at which this will happen, you need to care about that. If you don't do that, that won't work. And the first guy who realized that and set up standards to predict these things is Arrhenius again. And you will see here, this file here is actually something that we call Chemkin standard. In this world, there's been a nice effort in the community of combustion 30 years ago probably, where people have tried to organize all these schemes in the same way so that we can capitalize all the knowledge that people get. And so if you see here, this is the simplest scheme for hydrogen. You get 9 species and maybe 19 reactions. If you talk about gasoline, for example, instead of 9 species, you're going to have about 300. And instead of 19 reactions, you're going to have 3 to 4 or 5,000. Okay? And of course, now things get complicated. If you just want to solve the equations to understand those things, it's going to take quite a while. And this is a big part of combustion science. Not a part I'm working with. It's a painful part because, of course, when you get 4,000 reactions, if one of them is wrong, nothing's going to work. So it's an important job. Why is it difficult? Well, because flames are fronts, basically. If you look at a lighter or at the flame I've just shown you, it's something here where you have the initial gases, so for example, methane and oxygen, and then on the other side, you get the burn gases. And here in between, you have the place which is called the flame, and it's a flame front, so it's very thin. The thickness here is less than 0.1 millimeter typically. And in this zone here, everything will be happening. So everything I've shown you here, all these reactions will take place here in a very, very small zone. So if you want to understand what's going on, if you want to measure anything, if you want to compute anything, you need to be able to compute things which are extremely thin, where all the reactions happen extremely fast, and that's a pain. So just to make things clear, I have talked about thermochemistry and I've talked about chemical kinetics. I just want to make the difference between the two again. The thermochemistry deals with the initial and the final states. And it's totally independent of the speed at which one goes from one initial to final state. So it's basically you're taking the train from Paris to Toulouse. Okay? It's just saying that you're on the track from Paris to Toulouse. It doesn't tell you if you're going to go there in 1 hour or in 1 year. It's not the field of thermochemistry. It tells you if you keep going on that track, eventually you will reach this stage. If you want to know more about the speed, then you need to go to chemical kinetics. We'll come back to that in the next sessions, but on the displays here on the website, you can find more information on that and more examples. So chemical kinetics now, this is the science which will tell you how fast you go from one state to another. You're going from Paris to Toulouse, and you're going with the TGV. So, okay, it's going to take you 5 hours to do it. No, TGV, not everywhere. And to do that, you need to know much more information. You don't need to know only the track. You need to know which train. You need to know the speed of the train, etc., etc. So chemical kinetics is a little bit more complicated than thermochemistry. Okay, let's talk a little bit about what we're burning now. I'm sure everyone in this room has followed a course on aerodynamics. Okay, you have you have studied the Navier-Stokes equations, and probably you have looked at the pressure losses in tubes and flow around wings, etc. When you were doing that, implicitly, no one told you, but you were using a simplified set of equations. And in this course, I'm going to show you the full set of equations. You were basically studying only air. All the gas which was flowing for you was air. So it was a mixture of oxygen and nitrogen. So typically, probably you have seen that, you remember it. You have when you have this mixture for classical, what I will call classical air, you have 32 grams of oxygen here. You have 105 grams of nitrogen. So the total is here, and the mass fraction of O2 here in this mixture is fixed. It's always the same. It's the mass of O2 divided by the total mass. It's this famous 23% in mass in terms of oxygen mass. Now, the molecular weight of air is not 137, like I see that almost every year at the final exam. It's this number divided by 4.76, okay, because you need to know the weight of 1 mole. So it's the famous 28.8, sometimes you take 29 gram per mole. And in the state equation, when you are at P equal ρRT, R is equal to 288 joule per kilogram in Kelvin. And the CP of this gas is also of the order of 1,000 joule per kilogram in Kelvin. So this is what's been used in all the books and all the courses you have taken up to now. The problem is, in combustion, it's more complicated now because it's not only air we have. The air will change. Instead of oxygen, we're going to produce CO2. So we need to take into account the fact that we're going to burn things. So instead of these things, we're going to have a mixture with all these gases. As I said, between 100 to 3,000 species maybe. And so that makes our life more complicated now. We cannot only solve for velocity and pressure and all these things like you did before. We need to solve for what we call the composition. So what is the composition? Well, the composition is the equation which gives you the mass fractions of all the components in a gas. So what is the mass fraction? The mass fraction is, if I take this room, I measure how much mass of the key species I have, I divide it by the mass of everything in this room, and I get the mass fraction here. As I said, the mass fraction of oxygen, for example, today in this room must be of the order of 23%. Now the problem is that I need this YKs here for all the species in my gas. So if I have 3,000 species, I need 3,000 mass fractions. That means I will need to solve for 3,000 more equations. How do these equations look like? Well, this looks like this. I will come back to that in the next course. You have a term here which tells you how the mass of the key species is changing. Here you have the flux due to convection. And here you have two things you don't know for the moment. This is the diffusion velocity of the species scale. I will tell you what it is later. And this is the reaction rate. Of course, the reaction rate here, you are used to see this equation without these two terms. Okay, this is what you call the continuity equation. The continuity equation in a gas where there is no combustion just tells you that mass is conserved. Mass is flowing, you cannot lose it. Either you get accumulation of mass or it flows away to another place. With combustion, it's different. You can have an element where you enter with methane, and the methane will disappear here and come out as CO2. So this will take place through this term, which is called the reaction term. Now, reactions terms are determined by chemical kinetics, just what I've told you before. And the diffusion here of this term is something called transport. I will tell you also what this is soon. Let's start with chemical kinetics. This famous reaction rate in this equation, this one here. How is it written? Well, this is the job which was done by Arrhenius a long time ago. Arrhenius said, okay, if I have a reaction A plus B goes to C, what is the speed of that? He said, well, if I want to know the speed of this reaction, it's probably going to be proportional to the mass fraction of A. If there is no A, there is no combustion. Same thing for B. And then what he found is that he had to add a term here, which is exponential minus TA over T. TA is a constant. This is what we call the activation temperature. And T is the local temperature. So what does this equation mean? If you want to have combustion, if you want to burn something, you need fuel, you need oxidizer, and you need temperature. You see this term, if temperature is small, okay, this is an exponential minus something which is large, so this is 0. In this room, if I add gas, okay, if I fill this room with gas, nothing will happen. Okay, you might get sick, but no one will be killed as long as you don't have a hot spot somewhere. If someone then ignites something, or if you have a spark somewhere, if the temperature somewhere goes up, this term will go down, the exponential will go down, and then this thing will get crazy, and combustion will start. So combustion requires three things: the fuel, the oxidizer, and the temperature. And this is a very interesting property of combustion that we use every day. But it's important to realize that it conditions what we call the regimes of combustion. So what is the regime of combustion? The regimes of combustion are defined in the following way. It depends how you mix the fuel and the oxidizer. The simplest way to do combustion is what we call the premixed case. Premixed means you take A, you mix it with B, and then you ignite it. So typically, you take this room, you bring gas, you mix everything. Everything is ready for combustion, and then you ignite it. That's what you do, for example, in a piston engine. In a piston engine, classical piston engine, you fill the piston with air, you add the gasoline, you let it evaporate. When it's mixed, you ignite the spark, and you get combustion. So that's a very efficient way to do combustion. But there is one problem, is that once you have mixed the A and the B here, you just need a spark, and then everything goes away, everything burns. And that's dangerous, okay? You don't want to do that in terms of safety, of course. It's extremely dangerous to be in a situation where you just need the spark to get everything burning. So the other solution is to do what we call diffusion flames or non-premixed flames, in which case you keep the A and the B separately. You don't mix them, okay? This is what you do, for example, in a rocket engine. You know, you get one place where you store the oxygen, one place where you store the hydrogen, and you mix them at the last instant. You don't mix them before. That would be just suicide, okay? The funny thing about diffusion flames, if you look at it, I will show that, I think, in 3 or 4 courses. It's surprising that you can mix them at the same time and they will still burn, okay? They will burn at the same time as you mix them. They will mix and burn at the same time. The problem is that this is not very efficient. It's safe, but it's not very efficient. And this is where fluid mechanics come into our story. Fluid mechanics is what determines how you mix things. If you mix them before or if you mix them at the last moment, this is done by the way you have organized the flow. So to summarize this business about regimes of combustion, you have here these 2 classical regimes. The first one is the premixed, which is the most efficient, the less pollutant, but the most dangerous. It's called the bomb also, if you want, so if you have this kind of system. The diffusion of the non-premixed are less efficient, they are more pollutant, I will show you why, but they are much less dangerous. And the problem in industry is that we don't want to carry a premixed system with us. We don't want an aircraft where you get a tank with premixed gases. And we don't want that, of course, in your car. So we want to have something which is a diffusion mode. But still, if we want to make efficient, we want to mix it as fast as possible. So let me give you an example. This is a combustion chamber. This looks actually exactly like the one you had in your hands here. There is a place where we inject the fuel here. Here we get the swirlers when we inject the air. And in this zone, we mix the fuel and the air. We try to mix it as fast as possible. We store the kerosene somewhere. We get the air from the compressor. And we try to mix things here fast. The problem is that this was the design people had a few years ago. And in the combustion chamber, things were not really mixed, not mixed enough. It's like cooking again. If things are not mixed, you don't get a good result. So they thought, well, we should add an additional tube here. And the role of this tube is that the air and the fuel should mix here before they burn. And if we do that, we will have something which is more premixed here than here. And so we'll have a better flame. So in the idea of these systems, and they have been generalized under the name LPP, and I think most of the gas turbine companies have a system like this today, is that you would have here injection, here you would have mixing, and here you would have combustion. And like always, flames don't always do what you expect them to do, because if you start having a zone here where you have air and fuel mixed, what can happen is this thing. You can have what we call flashback. The flame, instead of staying here, the flame will see here that there is a way to propagate, and so the flame will come back and come into this system. And again, if this happens, this is the end of the system. I've shown you a picture like this before. This is an example. You had the flashback here, and you burn completely the injector. So how does this happen? Just an example of a very old LES we did here in a PhD maybe 10 years ago. This is a cut here. This is the axis of symmetry of the system I've shown you. Here we're injecting fuel. Here we're injecting air. You can see the cold gases here and the burn gases here. This is what we call a stable regime, where the flame will stay there. That means it's exactly the place where we want it to be. We have mixing here in this tube. This is the mixing tube from here to there. And the combustion, as you can see, stays exactly where we expect it to be. So this is a nominal regime. The problem with a system like this is that if you change, again, a little bit the regime, you decrease the power, for example, what can happen is this problem. Now you will see that we are decreasing the flow rates here, and the flame, instead of staying here, will have a bad idea of flashback and coming to this point. Now this is the end of the story here. And you can see that, of course, a system like this cannot be used in a real engine. It would be too dangerous. The system is too sensitive to a small change. So this is an example of where, again, we try to use a system and use the fluid mechanics to get a premixed flame here, but then we can have other problems. And again, we come back to what I mentioned before. Combustion instabilities are always very close to our problem. Same example here in a burner coming from Alstom. Alstom had designed a very complex burner a few years ago. Some of you probably are too young to remember that, but Alstom almost went bankrupt. When was that? 6 years, 8 years ago. And it may have been Sarkozy in that time who worked on that. But in the end, what happened is that all your parents and me paid for Alstom with our taxes to be able to avoid that this company goes bankrupt. Today it's doing very well. But at that time they had problem with this burner. And the problem with the gas turbine is that if you sell a gas turbine to a customer and the gas turbine is not working, it's making noise or it's vibrating, the customer stops the gas turbine, and then you have to pay for the money which is lost by your customer. And this is a lot of money. It could be typically 50,000 euros a day. So if you have 100 gas turbines in this world and they don't work for 100 days, you can multiply 50,000 by 100 by 100. You see right away that you're going to go bankrupt very fast. And so the problem with this burner is that it was, again, optimized to be very efficient in terms of pollution and efficiency, but it had problem of instabilities. It's a very complex system. I'm just going to show you an example of how it works. You have air coming here, and here you have fuel injection. And the way it works is that the system is staged. You're injecting air here, and the methane is injected here. These are all here small methane jets. You have many jets to try to mix things rapidly. Again, the objective is to mix things as fast as possible. So here you get the mixing tube, basically, where you mix the air and the fuel. And here you get the combustion taking place here. This is the reaction rate you see here. And you see here how the system works when it works the way it should. That means you have injection, mixing, and combustion. Now, this is the nominal regime, and this is the way it works actually today. Now they have fixed the problem. But in certain cases, you could have what I'm going to show you now. Instead of working that way, you would have this regime. It's another solution of the same Navier-Stokes equation, except here, again, you get a coupling with acoustics. And again, you see in this fluid mechanics problem where we try to optimize for combustion, we get into a problem of combustion stabilities. What's happening here? Well, basically, the acoustics get into the picture, and you have not at the same time, but you have injection, and then combustion, and then injection and combustion, and the whole system pulsates. These pulsations are not always a problem. For example, well, not a problem. One of the famous systems where we did, not we, the Germans actually did pulsating combustion on purpose was the V1 during the Second World War. They designed an engine which was designed to work in a pulsated mode. But if you don't want it, if you don't plan on it, of course it's a problem. If your system is not designed to resist it. And so in that case, that was the problem. And this problem was fixed. The problem is not you can always fix it. It's just that it costs money. Okay, I want to say something about turbulence now. You know what turbulence is. The problem is that turbulence also appears in combustion. This is a very, very old movie, probably 30 years, 22 years now. We did that long time ago, and our problem was the following. We have a flame here, fresh gases, burnt gases, and we're just sending turbulence into this flame. The first thing which happens when you send turbulence, this is vorticity here, into a flame, you can see it here, is that the flame gets wrinkled. It does not remain flat. The flame starts having all these funny shapes that you can see on it here. And it gets longer, and it burns more. And you see right away also that it gets very complicated. Turbulent flows, probably you have studied them at school already, are complicated. But when you add a turbulent flow with flames, then things get really tough. And when I saw that when I was your age, I went to see my teacher, professor there, and I told him, well, I'd like to do laminar flames, okay? I don't want to do turbulent flames because turbulent flames look very complicated. And he told me, well, it's not a problem. If you want to do laminar flames, you can study the lighter and the candle. If you want to do turbulent flames, you can study that. So I said, okay, I'll do turbulent flames anyway. Just no way you can make money on laminar flames, okay? A small amount of people do, but in practice, the real applications are all turbulent. Why are they turbulent? If you want a lot of power, you need a large flow rate. If you have a large flow rate, the flow will be turbulent, so the flame will be turbulent. There's just no way out of that. So all the practical applications in combustion will be turbulent, and as you will see, the turbulence makes things interesting. This is why we get paid, actually. Of course, as you know, combustion gets hot. I've said that before. Just to give you orders of magnitude here, in most flames, you have here a temperature of the fresh gases from 300 to 900 K. Why does it go up? Because usually we don't burn gas right away, we get it through a compressor first. So at the end of the compressor, because of compression, isentropic compression, you are hot already. The density will be of the order of 1 kilogram per cubic meters. And if you're at 1 bar, of course, in a real engine, you will be at 20 bar, 40 bar. If you're using a diesel engine, you will be at more than 100 bar. In a rocket engine also, you will be at more than 100 bar. When these things burn, you get to a second stage here, which is temperature of the order of 2000 K. And the pressure will be the same, but the density will be much less. If you just look at the state equation, if you are warm, you are light. This is why on Earth, if you do a fire, the hot gases go up, okay? It's just, it's good actually, because if they would stay there, you would have a problem. It's actually a problem for safety if you are in space. If you have no gravity, the burn gases remain where they are, which is not a good way to evacuate them. You have to push them away. The second thing, which is not as known probably, is that the burn gases are very viscous. You could see when you see them, in a fire, you see burn gases going up. They look like they are not viscous at all. It's not true. The viscosity, the kinematic viscosity, nu, changes like the temperature to the power 2. So typically, between the viscosity in the burn gases and the viscosity in the fresh gases, you can have a ratio of 10 to 50. That means the Reynolds number in the burn gases will be much less than it is in the fresh gases. And again, you will see this has implications for turbine combustion. Okay, I've talked a lot about gas combustion. Now, gasoline, kerosene are not gas, they are liquid. So when you put gasoline in your car, you put liquid. How does that burn? Well, you need to atomize this thing. And this adds a new dimension to the field of combustion now. We have to care about the following problem. How do we inject the gasoline into the engine? You cannot just take the gasoline and put it in your cylinder. It won't work. The important thing is you need to atomize it first. And once it's atomized, that means broken into small droplets. These droplets will go into the chamber. They will evaporate. They will go to gas. And when they are in gas, then we are back to the previous problem. We have to burn gas with air. The problem is that to do that, to atomize the droplets and to vaporize them, it's quite complicated. And most of you probably here are using diesel engines. The main progress in diesel engines in the last 10 years is something we did on the atomization by increasing the pressure. In a diesel engine, the pressure of the liquid when you inject it can be of the order of 1500 bars. And in the old days, it was much less than that. And if you have seen an old diesel engine, an old diesel car, if you're following it, for example, you get this black smoke out of it. And this was completely suppressed because they were starting to use these atomization systems at high pressure. In terms of science, it means we have a new problem now. We need to handle combustion and droplets. Now, droplets are very interesting animals. They don't necessarily follow the gas. If the drops are very small, they will follow the gas. But if you have a big drop, then it will go where it wants. This is an example of a simulation here by Vincent Moreau a few years ago. He's injecting here droplets in a gas where you have a recirculating zone here. And you will see the trajectory of the droplets is an interesting one. You see the droplets here, they come into the chamber, then they go backwards, and then they are convected away in this zone here. And at the same time they do that, they evaporate. And so if you need to predict combustion now, you have to care also about the droplets. And that's a very active field of investigation at the moment. This is, for example, something which comes from a PhD thesis, which was finished this year. Those are the new systems installed, for example, at SNECMA. This is called multi-point injection. Instead of injecting the kerosene at one point, you inject it at many points, many smaller points, to hope that the mixing will be better. Again, the objective is to mix very fast. If you look at a flow like this, this is what you obtain. It's basically a big mess. You have here all these small jets, which are droplet jets. They mix with the air, and you can see the droplets here in this chamber. The droplets, of course, are dispersed. They evaporate at the same time. We track each of these droplets, and you have to worry about its combustion. It's an interesting problem for simulation. Now you see, here you get maybe 2 or 3 million droplets in this simulation. Each of these droplets here has its own problem. And if we want to understand that, we need to care about one droplet itself. This is something else we do. For example, this is one droplet, and we are tracking the flow around droplets which are very close together. In certain regions, the droplets are so close together that you need to care about the interaction between the droplets. This is another aspect of combustion which makes things interesting. Okay, I want to talk a little bit about ignition. As I've said before, if you have gas and fuel and air, it's not enough for ignition. You need to ignite things if you want it to go. In a gasoline engine, you need to ignite it at each cycle. This is why you have sparks, okay, spark plugs. In a gas turbine, of course, in the gas turbine, you ignite it only once when you start the gas turbine. Then you have 2 ways to do that. You can ignite things by spark, or you can ignite it by auto-ignition. What is auto-ignition? Well, it's basically the fact that you don't use a spark, you just compress the flow. If you compress it enough, the temperature will go up, and at some point, combustion will start. This is what you do in a diesel engine. In a diesel engine, there is no spark. There is just a piston going up, up, up. At some point, the pressure is so large, then you can start having combustion without any spark. Ignition is a big problem. Of course, well, most of your cars now today, they start. You know, but 20 years ago, during the winter, you would start the car and it just would not start. So these problems are fixed, but if you think about aircraft, igniting an aircraft engine is not a big problem. The problem for an aircraft engine is to reignite it. What do we call reignition? It's a very important part of the design of an aircraft engine. Reignition is that you're flying and suddenly the engines stop. It would be a good idea if you would be able to restart them, okay, in a finite time. Let's say a time which is shorter than the time it takes to go down. And this happens, you know. It happens, you have seen with talking about volcanoes, for example. There were a few examples of engines, even 747, for example. Not this year, but a long time ago. 747 lost the 4 engines at the same time. Because the problem is the volcano is not really the ashes, it's the fact that there is no oxygen there. If there is no oxygen, well, combustion stops. You need oxygen. The 4 engines stop, and then you need to ignite them, reignite them. The problem is that you are very high. The pressure is low, the temperature is low, the reignition is very difficult. And this is the way you design your combustion chamber. The first criterion in an aircraft engine is that you must be able to ignite it again. In a civil aircraft. In a fighter, it's not a problem. The fighter engines are such that the reignition is almost impossible. So the pilot just pulls the trick and it goes out. It's too late for the plane. Now, of course, ignition is not only having ignition, it's also about avoiding ignition. If you talk about safety, a major problem quite often in safety is that people are working, for example, at ENSEEIHT, you know, they are working, redoing the buildings, and suddenly they hit a gas line, and you get a leak of gas into the air. Now the problem is, should we ignite it? Shouldn't we ignite it? Where should we be? If there is someone smoking there, is it dangerous or not? So in terms of safety, ignition is also very important. So this is just an example of combustion here in the lab again. In the laboratory, you get walls here. Here you are injecting air and fuel. I just want to show you how these things are ignited in practice. So this one is first the ignited view. You can hear the noise of these things as always. And this thing is ignited, it's blue, you see the flames, normal condition. How do you ignite that? Well, to ignite it, you use the spark. The spark is located here. You have only the air, 1 spark, 2 spark, 3rd spark, no ignition. And then it goes. Now, the characteristic of ignition in the system is that it does not happen at the first spark. Usually it takes a few sparks before it really starts going. Now you don't need to go to an experiment like this. If you want to study that, you can do it at home, okay? A system like this one to prepare your coffee is also an interesting problem where combustion has to propagate from one side to the other here. And even in terms of combustion science, it's not always obvious. Actually, some of you may have problems. Some mornings, these things don't ignite, you don't know why. It's enough, for example, if you have a dirty hole here, well, combustion will not be able to jump from here to there, and the whole system does not work. It can actually be dangerous if you have an old system, because then you have gas coming out of here, not burning, and of course, this gas will burn at some point later, and you don't always know where. So an example of what you can do today, the simplest example of combustion is the following for ignition. You have a jet of methane here into air. So it's exactly what would happen if I open this thing here. I will have a jet of methane into air. And the question which was raised here and studied experimentally by a few people, and we did an LES here, a large GD simulation of this problem, is the following. If I put a spark here, will it ignite or not? So I will show you 3 positions where we put spark. A spark very close to the jet, a spark here, and a spark downstream. So this is the case where the spark is very close to the jet here. The spark is here, and what you see is the temperature. And you can see here that ignition takes place. You see the flame is not starting here. The flame is what we called lifted. There is a zone here in which there is no flame. Mixing is taking place. I will come back to that later. And then the flame is stabilized here. So this is an example where you ignite the flame, and it works, and you get ignition. Another example here where we put the spark much more downstream here. It's a bit too far downstream, as you will see. Here you get ignition. You see there is something igniting, but the flow is going too fast. So the flame is igniting, but it's propagating downstream. Eventually it will go away and stop. So in this case, you can have a spark here. You won't be able to ignite this jet. The last case corresponds to exactly to the point which is the limit. And here you will have the experiment, and here you have the simulation. And you will see here that the flame is kind of hesitating. It's thinking, well, maybe I should propagate or not. So it's exactly, this is the reason why we are close to the limit. And you will see after a while, the flame will propagate and come back to its position here. Being able to predict this ignition is very important, as I said, for safety, and also to understand the fundamental mechanisms in this system. If you cannot predict here how ignition takes place, you won't be able to do it in what I'm going to show you now, which is a real engine. So when the thing is ignited, of course, it comes back to the same point as before. The question is, does it ignite or not? So now, I want to talk about helicopter engines a little bit. Helicopter engines are a different story. You don't reignite an helicopter engine. If the engine stops, you fall. Okay, that's the general idea. But you have to do something different with an helicopter engine. You have to be able to start your engine on the ground, but also on a mountain. And it's a very important aspect of helicopters. For example, for safety, they have to go up on a mountain at 5,000-6,000 meters. You have to be able to stop the engine and reignite it. And things get complicated. If you think about you go to India and you stop on a mountain at 5,000 meters, if you stop long enough, the engine will be cold, but the batteries will be cold, and the fuel will be frozen. Okay, and now if you're working for Turbomeca, for example, they ask you, okay, now I want to reignite this thing. Usually it's a tough work. One reason why it's difficult is that if the pressure is low and the atomization of the fuel is very bad, it's very difficult to make sure that you're going to be able to ignite one sector here and propagate towards the others. You have seen that in a real combustion chamber, we have sectors, many of them, and usually we don't put sparks everywhere. We use injectors at some point, and then we hope that the flame will propagate to the other points. And if these things work, you will see here how it happens. You're looking at an engine from the combustion chamber here. It's like you're sitting on the turbine, and you will see how ignition proceeds here. There is only one point for ignition here. You see the ignition started here, and then it propagated like this, and then the whole system was ignited. Let me play it again. So this is an experiment. The main problem for people building helicopter engines is that you do that on the ground and it works. You do that at 2,000 meters and it works. You do that at 4,000 meters and then suddenly the flame starts and stops here. or starts and goes there and stops again. And then you need to add a second ignition system. But you don't want to do that because it's heavy. On a helicopter, you know, the weight is really what you don't want to take with you. So it's a problem. You need to be able to predict when you will have propagation of this flame. So now it's not only a problem of igniting the first sector, it's a problem of knowing whether the flame will be able to jump to the other sectors. And that makes things interesting again for combustion science. So I'm just going to show you a computation here which was done 2 years ago on a full chamber, so that's a complete combustion chamber of Turbomeca, where you have all these igniters here, all these injectors, excuse me, which are injecting kerosene and air, and you have one igniter at the top, which is a jet of hot gases, and one igniter at the bottom, which is another jet of hot gases. And the question is, will this thing ignite or not? So in this case, it ignites. We picked up a case where ignition takes place. So you have here the blue zones correspond to high velocity. You have the injection here. You have the dilution jets. Here you have the hot injectors, these two guys here. And what is yellow is the place where reaction rate takes place. And so you see that reaction starts near the place where you inject and it starts propagating to the neighboring points. So let me show you the end of the movie now. So same thing here. You see combustion starting now, propagating, jumping from one burner to another. It takes about 20 to 40 milliseconds to do that. This is a case where things happen the way they should. It does not always happen like this, but when you have the simulation, you can understand why things don't propagate or do propagate. This is the same thing now. We're trying to understand how the hot zones propagate from one burner to another. We're going to travel with that. You have here the hot zone. This is an isosurface of temperature, and we're going to follow it. Now you see this part is hot, this is cold, and now we're traveling with the flame, and you see the flame is jumping from one injector to another, and finally it will meet the other flame which is turning in the other direction. Really, combustion, as I said, can be interesting. As you can see here, you get a nice mixture of transport, turbulence, chemistry, everything at the same time. An aircraft, this is an engine coming from SNECMA. Same problem, we need to ignite it. So here, as you can see, the design is completely different. You get injection of kerosene here, dilution jet, and the spark plug is located here. When you try to ignite this thing, this is what happens. You get the first spark and nothing happens. Then you will see there will be a second spark, and then this one will be able to produce combustion. And after a while, the flame will get stabilized. And again, this is what we study for reignition. So you get two examples here. Okay, I'm almost reaching the end of this introduction. Just to give you some background here, I'm sure you're going to work a lot on this course at home. So to do that, you can do a few things. At ENSEEIHT, you get 20 or 25 copies of the book here. This is the textbook where you will find almost everything I've said. You can also buy it on Amazon if you really want. But you can get it for free if you go to this address here. And at the same place, you will also find multiple tutorials and documents on the course itself. You will even find control and exams on which you can work. This is just a view of the website. When you go there, you can look, for example, this introduction will be here, and then the next courses, you will find them here. You also have some certain tools that you can use to train and to understand applications of what I've been describing here.